Hello everybody, thanks for coming. Let me introduce myself first. My name is Li An. I'm a staff scientist working in the section on magnetic resonance spectroscopy here at NIMH. So today I will first introduce some background knowledge on proton MR spectroscopy in the human brain. Then I will briefly describe 3 proton MR spectroscopy projects that we did in the past few years at NIMH. So the first project is detection of glutamate, glutamine, and glutathione at 7 Tesla. The second project is dynamic carbon-13 labeling of glutamate and glutamine using proton MR spectroscopy at 7 Tesla. The third project is simultaneous measurement of metabolite T1 and T2 relaxation times at 7 Tesla. So let's take a look what a MR spectrum looks like. This spectrum is acquired from a 2 by 2 by 2 cubic centimeter voxel in the prefrontal cortex of a healthy volunteer, acquired here at the NMR Center using the 7 Tesla Siemens scanner. So you see the highest peak at 2 ppm is NAA, N-acetyl aspartate. So the second highest peak at about 3 ppm is creatine. Then the third highest peak is choline at 3.02 ppm. So among the smaller peaks, glutamate at 2.35 ppm is the highest. Then to the left of glutamate is glutamine at 2.45 ppm. Then glutathione at 2.55 ppm. So ppm stands for parts per million. It's a measure of chemical shift. So in the field of MR spectroscopy, the ppm scale increases from right to left. So that's a convention. So basically, this is what a spectrum looks like. Every peak corresponds to a metabolite. So the concentrations of metabolite in human brain is roughly around 10 millimole per liter, or even smaller. The highest NAA and creatine is around 10 or 12 millimole per liter. On the other hand, the tissue water concentration is 35 to 52 mole per liter, which is about 4,000 times higher than the metabolite concentrations. This is why we cannot do imaging normally for metabolites because their concentrations are just too low. So low sensitivities is the main limiting factor of MR spectroscopy. Normally we do a single voxel or a chemical shift imaging of the metabolites, but the voxel size has to be at least greater than 1 milliliter to get a reasonable signal-to-noise ratio. So MR spectroscopy provides a measure of chemical composition of the tissue. So spectroscopy and imaging share the same physical principles. So here is a simple pulse sequence for MRS. This pulse sequence has no localization gradient. There's only one 90-degree RF pulse. This 90-degree excitation pulse tips the magnetization vector from the longitudinal direction to the transverse direction, then then the spins will precise about the main magnetic field B0. So the acquisition window is turned on immediately after the 90-degree excitation RF pulse to acquire the free induction decay signals. We call the free induction decay signal FID. You notice there's no magnetic field gradients are applied during data acquisition. This is different from imaging. In imaging, we use magnetic field gradients to do spatial localization. Here, there's no field gradients. As a result, the spectrum, which is obtained after Fourier transform of the FID, is a spectrum of different resonance frequencies of metabolites. The reason different metabolites have different resonance frequencies is because of chemical shift. So what is chemical shift? So when atom is placed in a magnetic field, the effective field at the nucleus is reduced from the external B0 field due to the shielding or de-shielding effect of the surrounding electrons. Then the electron density around each nucleus in a molecule varies depending on the types of nuclei and the bonds in the molecule. So the effective field at each nucleus and subsequently the resonance frequency of each nucleus will vary. This is called the chemical shift phenomenon. So basically, different molecules or protons at different sites inside one molecule may have different resonance frequencies. This is called chemical shift. So the resonance frequency of a proton is the product of gamma star of proton. Proton is hydrogen 1 times the B0. So gamma star is 42 megahertz per Tesla. So at 7 Tesla, the resonance frequency of a hydrogen nucleus, or we call it proton, is 300 megahertz. So the hydrogen nuclei in different molecules or different sites of the same molecule have different chemical environments. These different chemical environments will result in different electron shielding effects, so results in different effective field strength at the nuclei, then different resonance frequencies. At 7 Tesla, the resonance frequencies of different metabolites can differ a few hundred hertz, which are a few parts per million of 300 megahertz. So the chemical shift in ppm delta is defined as the difference between the resonance frequency of a nucleus and the resonance frequency of a standard compound, then divided by the resonance frequency of the standard compound. So the standard compound is often TMS. So chemical shift in ppm is independent of the external field B0. No matter it's 1.5 Tesla, 3 Tesla, or 7 Tesla, the chemical shift of different metabolites keep the same. Then at a higher magnetic field, the metabolite peaks will have larger separations in hertz because at 7 Tesla, the resonance frequencies are higher. It's the same chemical shift. The frequency difference in hertz will be larger, so this is good to distinguish different metabolite peaks in the spectra. In imaging, we only sort of care about chemical shifts, or we even don't need to care about chemical shift because we are getting signal from the water. It's water only. in spectroscopy, not only we need to care about chemical shift, we also need to care about scalar coupling, which is also called J-coupling. J-coupling is the through-bond interaction between the spins of neighboring nuclei. The spin of one nucleus polarizes the spins of the intervening electrons, and the neighboring nuclei are in turn perturbed by the polarized electrons. The J-coupling effect is observable if the distance between the non-equivalent nuclei is less than or equal to 3 bond length. So J-coupling determines the fine structures of peaks and also modulates the peak amplitudes. Let's look at the 7T spectrum again. So you see the NAA creatine choline peaks, they don't have J-coupling. Without J-coupling, they don't have any peak splitting. That's why they are called singlet peaks. So the chemical shift of this metabolite, NAA creatine choline, determines their position in the spectrum. Like NAA at 2 ppm, creatine is always at 3.3 ppm, choline is always at 3.2 ppm. And when you change TE, the peak amplitude will change due to the T2 decay. So it's straightforward. But then the other peaks, like the NAA aspartate peak at 2.67 ppm, the GABA peak, the glutamate peak at 2.35 ppm, the glutamine peak at 2.45 ppm, and the glutathione peaks, they are called multiplex because they have J-coupling. Here, due to fielding homogeneity, the peaks kind of broaden, so we cannot see the splitting. But if the field is more homogeneous, like in a solution NMR experiment, we can see the split. Each peak is split into several peaks due to J-coupling. So the J-coupling not only causes the peaks to split, but also modulate the peak amplitude when we change the echo time, TE. So at different echo times, the peak amplitude not just decay due to the T2 effect, they also varies periodically due to the J-coupling effect. So MRI and MRS are fundamentally governed by quantum mechanics. So MR imaging only acquires signals from water, so Bloch equation is enough. MR spectroscopy acquires signals from metabolites which have J-coupling, so density matrix is needed to describe the quantum system in a mixed state. Here I show a density matrix simulated glutamate and glutamine spectra. So in the glutamate molecule, the 5 carbons are labeled 1, 2, 3, 4, 5 different sites. So the proton carbon at one side will be called C1. Carbon at the second side, 2 side will be called C2. Then the protons at those carbon sides will be called, let's say, H2, H3, H4. Okay, there are 1 H2 proton, 2 H3 proton, and 2 H4 proton. You see the proton at each side will have a peak or some signals in the spectrum. You can see the 2 H3 proton have signals around 2.1 ppm. You see all these signals. Then the largest peak comes from the H4 proton. The 2 H4 proton have a peak at 2.35 ppm. This is what we will try to detect. And the glutamine H4 peaks are at 2.45 ppm. they are separate by 0.1 ppm. They can be separated on 7T but not on 3T or 1.5T because 7T have a more, because the resonant frequency is higher, they have more separation. Here, we only care about the coupling between the protons. So the protons, the neighboring protons, they are within 3 bonds distance, so they have J coupling. It's proton-proton J coupling, homonuclear. We don't have proton-carbon J coupling because 99% of the carbon is carbon-12. Carbon-12 have 0 magnetic moment, so there's no carbon and proton coupling. However, for that 1% of carbon, or if we infuse carbon into the human body, the carbon-12 can be replaced by carbon-13. Carbon-13 has a magnetic moment, so we can have proton-carbon-13 J coupling. We will talk about it later. Here, without carbon-13 infusion, we don't have carbon and proton coupling. We only care about proton-proton coupling. So how do we quantify metabolite concentrations? So B0 field in homogeneity will broaden the peaks, but they will not change the peak area. So when a peak is broadened, the peak amplitude will reduce, but its area will not change for most part. So peak area is a good standard for quantifying metabolite concentration. But when we talk about concentration, in most cases, it's a relative quantification. We use a ratio like NA to creatine ratio, glutamate to creatine ratio. A ratio is always easier. Absolute quantification is very hard. When the peaks overlap, then it's not straightforward to compute the peak area, so some sort of fitting is needed. A widely used technique in quantification is called the linear combination modeling. So FID, or spectrum of each metabolite, like for example, if we care about the 12 metabolites, which are NAA, creatine, choline, glutamate, glutamine, GABA, so we can generate a basis FID or spectrum of each metabolite using density matrix simulation or phantom experiments. Then the real data from a subject can be fitted by linearly combining the basis spectra. We call it basis sets. The basis sets normally have very sharp peaks, so we broaden those peaks. We may need to frequency shift those basis sets. Then we combine them to fit our in vivo data. Then the scaling factor for each metabolite will be proportional to the concentration of that metabolite. That's the idea of linear combination modeling. A commercial software is called LC model, which is widely used in the field. So the idea is we generate basis spectra for each metabolite, assuming they have the same concentration. Then we use this basis spectra, linearly combine them to fit your in vivo spectra, then see how much scaling we need to apply to the basis spectra. This scaling will be proportional to the concentration of that metabolite in the in vivo data. So this is a powerful technique because when your peak is overlapped in some region, they may not overlap in another place. So this is why this can help in quantifying the metabolite concentration. So when we do the in vivo spectroscopy, some kind of localization is needed, because without localization, it's very hard to make the B0 field homogeneous in the whole brain. It's simply not good enough. We need the homogeneity to be within, let's say, 10 Hz. So we need to localize a small volume to do spectroscopy. Also, we want to know the chemical composition of a specific spatial location. So one popular technique for localization in spectroscopy is called the PRESS, point result spectroscopy. So the pulse sequence have a 90-degree pulse and two 180-degree pulses. So the 190-degree pulse, 180-degree pulse, we can have a spin echo signal in the middle here. Then the second 180-degree pulse will refocus the spin echo signal. We have a spin echo signal here, the second spin echo. Then we start acquisition from second spin echo. So there's a slight selection gradient for the 90, 180, and 180 pulses. So each slight selection gradient select a plane. The three planes are orthogonal to each other. So the intersection of the three planes will form a rectangular prism. That's our selected voxel. Signals from outside the voxel are spoiled by the crusher gradient. So when we acquire the FID, the FID signal comes only from the selected rectangular prism, which is the intersection of the three selected planes. That's the idea of PRESS. Now I will talk about our first project, which is to improve the detection of glutamate, glutamic, and glutathione by minimizing the Na multiply signals at 2.5 ppm using a J suppression pulse. This is the pulse sequence. This part is a standard PRESS sequence plus a J suppression pulse that is proposed by us. And this part is for water suppression. Because the water signal is several thousand times higher than the metabolite signal, they interfere with the metabolite signal. So we use some 8 RF pulses, which is frequency selective, to spoil the water signal. So basically, the only difference between this sequence and the standard PRESS sequence is the J suppression pulse. So what is a J suppression pulse? Let's look at the Na molecule. So this part of the molecule is called acetate moiety. This part is the aspartate moiety. So this singulate peak at 2.0 ppm comes from the acetate proton. There are 3 acetate protons. That's why this peak is a singulate, not coupled to anyone, so it's very sharp. Then let's look at the aspartate moiety of NAA. At the two sides, there's 1 proton. So in the spectrum, this proton has some signals at 4.38 ppm. And then there are 2 H3 protons. So one H3 proton has some signals around 2.5 ppm. The other H3 proton has some signals at 2.67 ppm. The signals at 2.5 ppm is a problem for us because the glutamine signals are at 2.45 ppm and glutathione signal are at 2.55 ppm. This aspartate H3 signal interfere with the glutamine and glutathione signals. The way we want to eliminate this signal at 2.5 ppm is to apply a RF pulse frequency, which is frequency selective at 4.38 ppm. Because it's frequency selective, it will not affect anything in other places. However, due to the J-coupling of this H2 proton and these two H3 protons, if we select the right RF path, these signals at 2.5 ppm might be reduced. So in order to find out what's the optimal setting, like the flip angle, like the TE, TE1, TE2, we use density matrix simulations to simulate the NAA aspartate spectrum to see at what parameter setting those signals are minimized. So we developed a density matrix program by ourselves, which turns out to be thousands of times faster than existing program. The reason why it is so much faster is because we realize that we don't need to compute the density operators over 3D spatial point. That is very time consuming. Instead, we compute the propagator operators, and the 3 dimensions can be decoupled. So basically, we compute those in 1D repeatedly. That makes our program much faster. Gave us a very powerful tool. Other people are using supercomputers to compute like 1 week to get something. Here we just a few minutes we get something. Then we can just keep computing, then see what gave us a better result. That's a very powerful tool. So here is some simulations, like at TE equal 106 milliseconds, without the J suppression path, we can look at the NAA spectrum. It has a dip at 2.5 ppm due to the H3 proton. You can see the glutamate peak is at 2.35 ppm, the glutamine at 2.45, glutathione 2.55. If we sum them up, we can't really see the glutamine and the glutathione peaks because the big signals from the NAA overlaps with them. So with our optimized J suppression path, you see the NAA signals at 2.5 ppm are almost all gone. Then when you sum up all those signals, we can still see the glutamine peak and the glutathione peak. So this is the simulation. So are our simulations really agree with experiments? So we did a phantom experiment. So this spectrum is obtained from a sphere containing NAA solution. The solution is heated to 37 degrees Celsius. Then this spectrum is obtained by density matrix simulation, then fitted to the spectrum. You see how well the fit becomes. All the details agree. I was surprised how accurate it is. So basically our simulation agrees with the experiment really well. Then these are in vivo spectra from 8 healthy volunteers. So the spectra were acquired from the prefrontal cortex, gray matter region, and the right frontal lobe. That's mainly white matter region. So you can see the quality of the spectra was really good. Other people cannot get a spectra like this with a sharp glutamate peak and the glutamine peak are visible. You see the glutamine peak, the glutathione peak. And it's also very clear the glutamate peaks in the green matter is higher than in the white matter. You can see the glutamate peaks here are higher than in the white matter. So that's our first project I want to talk about. Oh, these are the fit. So still we choose one spectrum to show you the fit. So that's the in vivo spectrum on top. This is the fitted spectrum. This is the baseline, then that's the difference between the in vivo spectrum and the fitted spectrum. So the difference is relatively small. It means our modeling is pretty good. Here, this one is the glutamate, the fitted glutamate peak. This is the fitted glutamine peak. This is the glutathione peak. So this is called linear combination modeling. So basically, the in vivo spectrum is fitted by a linear combination of NAA, glutamate, glutamine, glutathione peaks, glutathione spectra, which are simulated using density matrix formalism. So these are the relative concentrations of different metabolites. Now I will talk about dynamic carbon-13 labeling of glutamate and glutamine using proton MRS. So in vivo measurement of glutamate and glutamine turnover from intravenously infused carbon-13 labeled substrates is a powerful tool for investigations of energy metabolism and neurotransmission in the human brain. So we want to demonstrate the feasibility of quantifying the time courses of the carbon-13 labeled glutamate and the carbon-13 labeled glutamine during intravenous infusion of glucose, carbon-13 labeled glucose. So basically, when we give intravenously infused carbon-13 labeled glucose, to the human body, there's no difference between carbon-13 glucose or carbon-12 glucose. So glucose is a source of energy. It will be quickly absorbed by the human body, and the carbon-13 can be transferred from glucose to glutamate, glutamine, and other metabolites. So we want to see the turnover of those carbon-13 from the glucose to glutamate and glutamine, if possible. So we scanned 8 healthy volunteers. So for each volunteer, we do a baseline MRI scan without any infusion of carbon-13. Then we started the intravenous infusion of carbon-13 labeled glucose. During the infusion, we scan repeatedly to get a time course. Each scan lasts under 6 minutes. So let's see how it works. This is simulated spectrum. Okay, on top is a glutamate spectrum without a carbon-13 infusion, so there's no coupling between carbon and the proton. We have the regular glutamate peak at 2.35 ppm. After the carbon-12 in the C4 site is replaced by carbon-13, this peak at 2.35 ppm will disappear because of the decoupling. Instead, a peak at 2.55 ppm will arise. This peak will arise. Also, there are some small signals on this side. The glutamine signal is similar. This peak will disappear once the carbon-12 is replaced by carbon-13. Instead, at 2.65 ppm, a glutamine peak, which is labeled by carbon-13, will appear. So these are the spectra we got from one healthy volunteer. The top one is a baseline spectrum. There's no infusion hasn't started yet. Then the other spectra are spectra during the infusion. You see 9 minutes after the infusion starts, 18 minutes after infusion starts, up to 79 minutes after infusion starts. We look at here. We look at the glutamate peak. It becomes smaller and smaller. Why? Because once the carbon-12 is replaced by carbon-13, that peak will be gone. at the end of the infusion, the peak is much smaller because most of the carbon-12 are replaced. I mean, carbon-12 in most of the glutamate molecules are replaced. There are still some molecules are not replaced by carbon-13. Then we look at the glutathione peak at 2.55 ppm. It becomes larger and larger. It's not that the glutathione becomes larger, it's because the peak, the glutamate peak, carbon-13 labeled glutamate peak is getting larger and larger. More and more carbon-12 glutamate is replaced by carbon-13 glutamate. If you look at this again, that's this peak. It's not the glutathione peak. If we do a subtraction between the spectra during the infusion and the baseline spectra, we get all these different spectra. We can see there's a negative peak at 2.35 ppm. This is the carbon-12 glutamate signal. It's decreasing, so after subtraction it becomes negative. This positive peak at 2.55 ppm is increasing because carbon-12 is replaced by carbon-13. This is the carbon-13 labeled glutamate signal right here. So by fitting this different spectra, we get the concentrations of carbon-13 labeled glutamate and carbon-13 labeled glutamine during the infusion. This is a plot of the concentration of carbon-13 labeled glutamate and glutamine during the infusion. We can see it keep going up for the glutamate. So at the end of the infusion, over 60% of the glutamate carbon-12 were replaced by carbon-13. So from this figure, we can see the turnover rate of the carbon-13 from glucose to glutamate. So we basically have a measure of the metabolism. So this could become a powerful tool in some, let's say, cancer patients. The third project is a simultaneous measurement of metabolite T1 and T2 relaxation time. So in prior studies, the metabolite T1 and T2 values were measured separately using different pulse sequences. So we use a pulse sequence to measure T1 first, then we use another pulse sequence to measure T2, and the measurement time is very long. And when we compute T1, we don't use the data from the T2 measurement. When we compute T2, we don't use the data from T1 measurement. So they are measured separately. Here we propose to measure metabolite T1 and T2 simultaneously. So this is the pulse sequence. This part is still the trace sequence with the J suppression pulse. This part is the water suppression pulses. Then we add two broadband inversion recovery pulses. The first one is just to null the magnetization vector at the beginning of each TR to make them zero. This inversion pulse is with a variable inversion time is used to encode T1 information. This is basically an inversion recovery pulse. So in our pulse sequence, we use 30 different sets of acquisition parameters. You see the TE at the beginning is 60 milliseconds. We acquire 4 acquisitions. Each acquisition takes 3 seconds. Then we do the 60 millisecond TE again, but the TE1 is changed from 30 to 37 milliseconds. We acquire 4 acquisitions. That's another 12 seconds. Then we change the TE to 70 milliseconds, 80 milliseconds, 90, 100, 110, 120, 130, 170, 220, and 230 milliseconds. During the when the T is 70 and 100, we also apply the inversion recovery pause with a variable TI, time of inversion, to encode T1 information. So basically, we acquire 30 sets of data simultaneously with T1 encoding and T2 encoding. Then we can, how do we choose these TE values? We use simulation. So these are the simulated glutamate and glutamine peaks at different TEs. We can see at a very short TE, the glutamate peaks are not very good. They are broad and have a low amplitude. It's not good for quantification. So we start our TE from 60 milliseconds when the glutamate peak becomes reasonable. You see the glutamate peak keep increasing and keep being sharp until 130 millisecond TE. Then it becomes very broad. When the glutamate is broad, it overlaps with the glutamine peak, so it's not good. So we don't acquire anything here. Then later, it becomes sharp again. That's how we choose our TE values. So our basis sets are also need to be computed for each set of TE. We have 30 sets of TE. When we generate our basis sets using density matrix simulation, we have to generate the basis set for each metabolite and each parameter setting. That's why computation speed is important. When we quantify the data, we also developed a two-passage fitting approach. In the second passage, all 30 sets of spectra were fitted together. These are the spectra from the 30 different sets of acquisition parameters. The whole thing takes about 10 minutes to acquire. On top are the data, then below the data is the fit. You can see the fits match the data really well for each parameter setting. The negative peaks are caused by the inversion recovery pause. So for each set of parameter, the density matrix simulated basis set can fit the data very well. From this data, we can get the T1, T2, and the concentrations of each metabolite. So we can see in the gray matter basically in the prefrontal cortex. The white matter comes from the right frontal lobe. So in the gray matter, the T1 is shorter and T2 are longer. Two things we found that is interesting. One is the T2 of glutamine is much shorter than the T2 of glutamate. And the other interesting thing is glutathione have a very short T1 compared to other metabolites. You see the other metabolites T1 value is over 1 second, but the T1 of glutathione is only 490 milliseconds. This is due to the presence of a sulfur atom in the glutathione molecule. So compared to conventional methods where T1 and T2 are determined separately, the proposed method has smaller variations in computed T1 and T2 values because information from all collected data was utilized in computing both T1 and T2. Thank you for your attention. Any questions? All right, thank you.